Thank you so much, Brian, and I'm very honored to take the stage in this capacity, given the people who got before me, so it's a real pleasure to be here. I have only 50 minutes, which is, of course, or something like that, which is much better than the other speakers, but let me jump right into it. First of all, there's no paper that's called the price and tail risk and equity premium across the globe quite. It's because it's a symbiosis, it's a collection of facts and results from a bunch of papers that I have not written myself, but in collaboration with a bunch of people. I should say maybe foremost Victor Todorov, who's in the audience, my colleague at Kellogg. He's, as we see on the next page, can co-author on more or less all the papers this builds on. Nicola Fusari was at Kellogg as a postdoc for a couple of years, a leading visiting scholar. He's now doing well at Baltimore, at the business school. Rasmus Vaneskov is a Danish scholar. He's at CBS, also at Nordea Securities, I think, which is the largest Scandinavian bank, so he works there part-time. But he visited us for a while, and Masato Okata is at the University in Tokyo, and visited us for 1 year as a visiting scholar as well. So we caught some of the people who came through Northwestern and kind of said, we should work on this. He's very skilled, so it's been a real pleasure to work with these very bright people and develop somewhat of a coherent research agenda on options and volatility and tails and equity premiums. So I'm going to build on a bunch of stuff. That's kind of what I intonated first. And so we spent a number of years thinking about what is a natural kind of metric framework to build for drawing inference from options. Options is a panel, right? In the sense that you have a surface which has a time dimension in terms of time to maturity and strikes, but it also, you observe it many times. So it has a time dimension, and then there's this cross-section in some sense. It's highly unbalanced. You don't never see the same unit again, meaning an option today has 10 days to maturity, tomorrow it has 9. It's not the same quantity. So it has a lot of inherent challenges. People in the past dealt with it in many different ways. We thought we found a very good way of doing that after experimenting for a long time. So that's that paper. I'm not going to today talk too much about the technicalities of how we estimate the things and draw inference. But if somebody gets really excited about this, that's a good place to go back and look. Although, given where it's published, it's very synthesized and it's kind of maybe hard to dig into, but they force you to kind of make it very condensed. It is actually, this is generalized in this paper here, where Vaneskov was also, and is forthcoming. So that kind of makes more of a unified setting. This one had fixed time to maturity. Now we're going to allow maturity. So it has a panel data literature with N and T going to infinity. That's kind of what we're assuming that one. So the one that had red lines under it is kind of underlying my talk more than the others. We have this thing about the weekly options that the SIBO has been primary driver in introducing. They turn out to be extremely useful for understanding how to separate volatility and jumps from each other and thinking about separate pricing and thinking about how they separate risk factors and things like that, which is a point we made. But we've actually been greatly helped by the fact that weekly options now are very liquid. Yeah, let me not talk about that, but if there's no volatility piece, then maybe there's infinite activity jumps and other things. But here, there are 2 papers that are not published, and those are basically the ones I'm going to focus on, is to talk about something that at least a little bit new. I'm sure some of you have seen presentations by myself or Victor or Nicola on some of these issues, but what we're trying to say is that the evidence that we found in this paper up here, which is what are the actual risk premiums that are embedded in the index options that tell you something about people's appetite for taking on equity risk. And we kind of identified that there's a part of the surface that tells us a lot about that is actually robust when you go across the globe. So that's where the across the globe comes from. We have one that deals with Europe, or European indices, and one with the Japanese index. So that's where I will want to get to as quickly as I can. Okay, so what are the main points going to be in my presentation? First of all, and this is going back to that original kind of econometric-y type work, inference from options can be greatly helped if you apply the right panel data type techniques. and you think about also high-frequency volatility measurements, and you kind of merge the two, and especially it turns out a lot of techniques from high-frequency inference and volatility can be applied in that cross-section as well. And we want to push that, but again, I'm not going to spend too much time otherwise today talking about that. What I will emphasize much more is the option panel. Using those type of techniques will help you find features in terms of risk premium and how different interesting risks are priced by investors that you can't see from the underlying asset. And in the past, when there weren't that many options, or options were hard to deal with in terms of econometrically, people used the underlying to back out what is the volatility, how do the jumps dynamics work, and they kind of took that as given, and then first they went to the options. What we want to advocate is you go and look at the options, because if you start identifying state variables just from the underlying, you're going to miss a heck of a lot. So kind of want to reverse that. And the short-dated options offer particular advantages, especially because it allows us to separate these jumps and volatilities. And I'm going to emphasize tails. Victor is a co-author. He's Mr. Tail and Mr. Jump. And I certainly learned from him that there's a lot of weight. Once we control for the tail, the variance risk premium doesn't seem to add much more. So I'll be very much more specific about that. But the point is, the variance risk premium is a predictor, but sometimes it doesn't seem to do so well. It's a little bit non-robust. It gets much more robust when you identify a certain piece, a small, relatively small piece of it, and the rest of it doesn't do much good. So you get a kind of noisy indicator from the variance risk premium is our statement, but it captures something because embedded in it has this tail risk measure. Okay, and then I'm going to argue it holds up internationally. You can do it. You can do it parametrically and non-parametrically. That's another way of looking at robustness. You could like our parametric model or not, where we can use the information in all the options, or we can go short-term and do some more non-parametric, and we get very qualitative, consistent results with it. Okay, so enough talking in terms of introduction. Let me illustrate what I mean by the options pricing exercise being a panel data exercise and being very unbalanced in some sense. So this is actually a relatively short sample because for the S&P 500, because we could use many more options, we could go back in time, but we synchronized this with the European options data, and we did not feel comfortable going further back than 2007. So what you have on the left here is, just for illustration, the S&P 500 options that in our sample that we are using for our estimation purposes on the first day, which is very early 2007, and then the last day of a sample, which is at the end of 2014. And you can see here there are 6 different maturities trading. At the money is right around here. And what is plotted is the implied volatility. So it's just a different way of talking about the priciness of the options, right? And those of you who work with options know that once we go in the tail, yeah, we have this skew for the index options, and it's much more expensive for these out-of-the-money put options than it is here at the money. But this is what the skew looks like. You can see there's 6 maturities trading, but there are actually several hundred quotes. So it's a very liquid market. Go back, now go forward a lot. And this is recent. And you can see here are the weeklies, right? It's essentially 1 day, 3 days, 5 days, what have you, out. They are quoted options. And they're quoted much more liquidly than they used to be in the old days. So there's an enormous amount of liquidity here at the short end. You can basically look at that risk-neutral return distribution 1 day, 2 day, 3 day, 4 days out, more or less. And as you go further out, there are obviously gaps, but you still have an enormous amount of liquidity at certain maturities out there. So the idea is, how do you draw the maximum amount of information out of these things, and how do you get the salient features that we want? Clearly, when you have one underlying observation at the end of the day from yesterday, you have here shift in 800 or 1,000 options instead that are forward-looking. So they should be very informative relative to what's happening. So to, again, explain where we're going, the option panel is going to tell us that what happens out here in the tails is driven, it shifts around in a way that's different from how the at-the-money volatilities shift around, like Schultz implied, how the pricing shifts around. The standard option pricing model with affine models, if you go back and look in the literature, would typically identify on the underlying 1 or 2 or 3 volatility factors or something like that. The jump intensities would be function of those volatility factors in an affine way, and hence you could price these things using the affine model structure. Now, that meant that the volatility factors were driving also the tails and the jumps, which is what is priced in the tails. And what we find when we're looking at these things is that when we go across days and we see the dynamic of these things and we see the dynamics that's governing things in here, that they are not aligned, certainly not in a linear fashion. They're highly correlated, but at the money goes up, out of the money goes up as well, but in a different degree, and they can be, that shift usually decays over time. It decays much more quickly at the money typically than sometimes out of the money, and it does it to varying degrees over time. It's telling us something different. All these investors buying all these options or taking positions in them have a reason to price them differently at different times relative to at the money, we think. Okay, so what we're going to find is that the tails need a different treatment, and what we did in that 2015 paper is just, well, if we're going to stay within the same framework, we just need a separate factor. We cannot have a volatility factor. We need a separate tail factor to account for that. And we're going to let the option data tell us things. We're not going to rely on the underlying. And once we look at the options, it's absolutely clear that you need something separate to drive these things around. Okay, so what we found is that that left tail factor, when we started looking at it, is the one that helps you predict the future returns. Broadly speaking, the variance risk premium is supposed to do that. Well, it seemed to us that a lot of that came from that left tail factor, the one that you would actually miss if you just modeled from the underlying and you extracted the volatility factors, because that doesn't capture this variation up here. So the options become pivotal for us to come up with this empirical finding. Okay. Another thing that was, and this I didn't expect at that time, that left jump tail turned out not to explain future jumps or future volatility. It's as if this thing out in the tail is whipping around in a way that doesn't help us forecast the risk of the underlying going forward. Whereas the at-the-money options, the implied volatility of these different factors, they are very good at that. And that's exactly what people find when they model the underlying. They find other factors that help forecast the risk going forward. But if that tail factor is moving around and you're just estimating the underlying, you're not going to get that feature. What we say is that that actually seems to indicate what people require in terms of compensation for holding equity, but it's not directly related to where they think the risk is. It's a pricing of the risk. So that's where we're going. Okay. What that actually implies is that these deep out-of-the-money put options, that sometimes people question whether that's priced in a sensible, rational way, and whether we can explain it with economic models, and it turns out to be hard. There are papers, Oleg has a paper that literally talks about the, can we figure out what is going on with the expensive pricing of put options and things like that. Well, it led a lot of people to say that segment of the market is hard to deal with because if you're selling those options, you have to hedge with your exposures. It might be segmented from these things. Well, if we are right, then it's not at all segmented. It's actually speaking to the compensation people want for holding equity risk. And that means you have to find a different rationale. You have to think of time and risk aversion, financial intermediary constraints. Those guys who will usually do this gets a big financial shock because there's a crisis or something and they lose money. Well, then maybe some other people have to come in. Capital is slow moving. Compensation goes up. They have shortage of capital. It could be heterogeneous agents, and the most risk-loving are willing to do this just as out of the market because they got hit. They are financially constrained. Other guys have to come in, and they have different theoretical models that you could add to this. We are not going to take a stand on this. This is more of a traditional reduced form. It's a structural model, and you're going to parametrically put some structure on it, but it's reduced form in the sense we're not explaining where the fundamentals that are getting priced are coming from. Okay, so I already said we found this evidence for U.S. stocks and options. Now we're going to explore European and Japanese markets because people, that's the only way into robustness. We can't go further back in time. That the options data, especially in terms of being liquid, are just limited to somewhere in the late 90s or something like that. So we go international, things are not completely uncorrelated there, but at least it helps us speak to the robustness issues. We can also start pondering, you know, are these tails and these tail risk premia connected internationally? Is there a global factor or not? You can kind of speculate about that. I think the fact that there's currency translation going from one index to the other when you're going nationally, internationally, is a little bit of a hindrance, but you can certainly get some suggestive evidence. So let me then, with this introduction, jump into the evidence. So we're going to look at a bunch of European indices. These are the ones we found from Option Metrics at that point in 2015 when we were doing this, I guess, where they were liquid enough that we felt comfortable in including them. So something was going on with the French, so there's no French index there. I don't know why the Spanish and Italian was a little bit better. The Spanish and Italian indices over this period from 2007 up to 2014, and into 2014, were reasonably liquid, and they are interesting because there was a sovereign debt crisis in Europe, and they displayed a little bit of a different exposure to jump and volatility in terms of people's expectations once the sovereign debt crisis hit. So this is an interesting period. You have the financial crisis, and then you have the sovereign debt crisis, and you have an enormous spread in the performance of these European indices. You can see the DAX actually did quite well. If you accumulate from 2007 to the end of 2014, it went up by about over 50%, which is, this is with reinvestments of the dividends, but you know, that's overall not a bad performance given that you went through the financial crisis. They really recovered. The S&P 500, of course, also did very well. Later on, I'm sure the S&P has crossed by the gaps. You can see the FTSE was kind of okay. The Swiss index is here, but the Italian index is down 50%. So if you had put money in the Italian index in 2007, you were still down 50% 8 or 9 years later. So no wonder that the Italians are particularly mad at their politicians and the way the country is run and don't trust authorities and what have you. I really think there's a lot of political economy in even that point. But the Italians were almost wiped out in some sense in terms of equity investors. The Spanish index also did very poorly, but at least it recovers to around zero. But the point is there's an enormous spread here. I'm going to propose a measure from the options, a kind of a risk indicator, if you want to think about it, that does help you predict future returns. That is very different from telling you I can explain what the size of the equity risk premium is. I'm not going to say that. I'm not going to say it's 6% or 10%. In fact, you look at Italy, you know, you get this near minus 50% over 9 years. Does that mean the equity premium was negative and significantly negative in Italy? Of course not. It just happened to get shocks that were particularly bad for them, and maybe they got more shocks as well. So it was not expected, but they got some bad shocks. It can still be that this options indicator after the shocks tells you, well, relatively speaking, it's going to do a little bit better going forward than it did before. And that's the type, it's a correlation thing that we are after. So whether these things correlate in the right way over time. It's much easier to measure correlations than means. That's really what it is. Okay. So I am postponing talking about the model a little bit, because then everybody who doesn't, you know, feel completely comfortable with continuous time representations of option returns and volatilities and stock returns will maybe also kind of see where I'm going. But for those of you who want to see the model, it's coming. I will at least flash it up there and you can ask questions. But what I'm going to say is that for the European paper, we focus on a simple parametric model. And it really is simple. You're going to have only two factors. I know that's not going to be well specified, meaning maybe jumps can be captured by one factor, but if you want to be really good, you probably should introduce more. But certainly the volatility is not just a one factor model. We are going to focus on that because it's going to allow us day by day to very easily separate out volatility and jump factors. For some of the European indices in particular, that's actually relatively critical. We still think we absolutely get the salient features we have, and one of the other papers show that if you use the simplified models versus a more complicated we want to have for the S&P 500, you get essentially the same evidence for the jump factor. It's essentially, it maps 1-to-1. So at least the jump piece, which is going to be very important for us, is very well captured, we think. Okay, so the two factors is postulated to capture the dynamics for the whole option surface over time. It's going to be two factors that vary that explains to you why the shape looks like that. And then we look at the shape and we back out what are those two factors on a given day, and then we can go next day and see how it is, and you can start thinking about the dynamics of it and things like that. Okay, so the one factor is going to be spot volatility, and that kind of captures the small movements you see in returns. And then there's going to be this spot jump intensity. Now, there can be positive and negative jumps to the index. It turns out investors really care about the negative ones, whereas the positive ones is just gravy. But as far as we can tell, all the interesting dynamics and what's really priced in a very different way is the negative jumps. So people seem to really care about negative events to equity when they are forced to have an exposure to equity. That's what they really worry about. And so it turns out, without losing explanatory power, we can simply let the propensity to get negative jumps be the thing that varies over time. And the positive jumps, well, just make it a constant. That is first order about what you get from the risk neutral densities we look at. So you could finesse that, but it's not going to change the results. Okay, we do not make any assumptions about the dynamics of the actual underlying S&P 500. We're all going to operate under the risk neutral density. Okay, so we actually, going back to some of the very earliest financial engineering option pricing papers, just model the whole thing on the risk neutral density. But we are going to link back, of course, to the expected returns and things. So that's a big difference. Okay, so assuming that you're buying the fact that I can look at an option surface on a given day, I can back out what is U and V, V being my volatility factor, and U is going to be this intensity with which we will see jumps in the negative direction. And we're going to put an exponential distribution on that, but it's going to be the intensity with which you see these bad events. Then you can back these out over time. So this is literally what we get if we do it. This is the volatility factor. Our spot volatility factor, of course, is high in the financial crisis. It's high here and here, which turns out to be kind of the sovereign debt crisis hit. This is my jump intensity factor. The two should be very correlated, meaning as you were going through the financial crisis, yes, people knew that, or thought that there would be a higher probability of bad events. At least they priced that into the options. What you really see is that there was a little spike here. This is the kind of first sovereign debt crisis phase in Europe. The tail index reacts much, much, much more sharply than here. And for the second piece, well, it's a little bit more here, but it's even more distinct here. So you see these more distinct spikes, and they're kind of slow to decay relative to what you see in the spot volatility. So that's what we get. They're highly correlated, but they have quite different characteristics as well. Now, it's a little bit annoying when you're running regressions and you have two very correlated factors, which is accounting for what? The traditional literature says the spot vol, or several components of the spot vol, is what matters, right? So what we're going to do is we're going to retain this and let it explain as much as it can. And then we're going to say, whatever is not in there but shows up in my U factor, my negative jump factor, I'm going to just extract that auxiliary explanatory power. So basically, the span of this guy and this guy would be the same as the span of this guy and this guy. And this guy is what I get if I regress this guy on that guy. So I'm just looking at the deviations from what's here. So basically, this is what qualitative, what is in the jump intensity that we extract that is not in the volatility. And you see, obviously, these spikes here. You see the much slower decay in volatility in the factor following these big spikes. So there's some lingering high pricing of the option tails versus the middle volatility in those periods. Now, are we going to say later that should be correlated with people expecting higher returns? And it's not linked to the amount of volatility you see, which is a good forecast of the actual risk that materialized in the future. But there's some compensation that can't be explained by that factor. So, what do we get? I'm just going to highlight these results. I've said it already a couple of times when we run these predictive regressions. So this is an affine setting. I'm actually not gone outside of the affine framework. So when I show you the model, you will see that it is an affine model, just that the jump factors added in on top of the vol factors, but in an affine way. So we can do all the same pricing tricks, and specifically in these type of affine settings, you should get that the excess returns is linked, linearly or affinely to the state variables that control the dynamics of the system. So we run these traditional predictive regressions where this is the excess return. We're running it on this volatility, spot volatility factor, and then this U tilde is this orthogonalized jump intensity factor. Okay? So we're running this excess return regression, and we care about whether the future returns on average has a positive loading or has a positive loading on these two factors. We do the same thing for realized volatility, which is of course a combination of the diffusive volatility and the jump volatility, just adding the squared jumps. So we're simply constructing the very simplest realized volatility measure going out 8 months from today, and we are getting the loadings on the same two factors. So here's what you do, what you get from the excess return predictability. So this is over the sample forecasting the future equity excess returns, or the equity risk premium. And over the first 5, 6, 7, 8, 10 weeks, you don't get that much, but then you get into a very highly significant scenario where these coefficients look statistically significant. And then it decays a little bit at the end. I don't want to put too much emphasis on half a year because our sample is somewhat limited, but that region here, out 3 to 4 months, very robustly comes in with a significant coefficient. But you can see one of the coefficients is always insignificant, and it happens to be the volatility coefficient. So the volatility does not help you forecast the equity returns. It is this auxiliary explanatory power that comes from the jump factor, where we have taken out everything I could explain with volatility as they covary, and I'm only looking at the excess movements or the orthogonal movements of the jump factor. So that shows up highly significant. If you look at the R squares of these things, it comes pretty high, up towards 20%. And here's the vol factor, essentially nothing. Okay, now that's fine. That might be that that tail factor is very good at explaining the risks that I see. So it's just, it turns out the tail is really good to predicting the risks. Well, here we're doing this thing where we're predicting the return variation going forward, and that is actually pretty simple. When volatility is high, it's going to stay high for quite a while. So you expect to get high R squares, especially when you have a crisis or several crises. And you get high R squares, right? You get over 60%. But it turns out my jump intensity, this orthogonal jump factor, does nothing. It's all now related to the volatility factor. You can kind of think of that as the implied volatility of very short-dated options. So if people are correct when they say, I have these RV measures, I can forecast realized volatility going forward using my RV measures. But if I compare that to the IV measures, well, it's a very tough competition. There clearly is extra information in the options. There might be some in the underlying. That's very consistent with this. The implied volatility is good at forecasting the future return variation. And the tails have nothing to do with it. At least you can capture it all through that volatility factor. So what are you getting out of this? You're getting a complete separation between the factors that seem to drive the risks, which is the volatility factor, and then the risk premium, the one that predicts whether you're doing better or worse going forward through the tail factor. The tail factor doesn't help you predict the risk, but it says something maybe about the compensation people demand at a given point in time for holding equity risk. And it shows up in the option surface out in that left tail. Okay. So I guess that's it. I will point out that there's a long illustrative or long historical literature on it's difficult to relate the mean and the variance in the stock market with each other. Some people can find support for that, some people overturn it, they have different instruments, they have different sample periods. It's very difficult to figure out. It's very consistent what we're finding here. We're finding it's very difficult to say that the volatility I see rationally going forward is directly linked to the compensation or the return, excess returns. But there is a part of the option surface that might help me say something about that. So what we think we've done by focusing our inference on the option surface, not the underlying, is that we are letting the option data talk to us. We're not letting the underlying tell us what the factors are that are relevant for understanding the equity risk premium. We are letting the option, where people are pricing risks and expected risks, speak to us, and we're trying to decouple the two, figuring out. And the decoupling worked actually more dramatically than we ever thought when we started doing this some years ago. So anyway, separate dynamics for the left tail and the jump factor and the jumps, time-varying pricing of jump risk. That seems to tell you something about how equities might perform going forward on average. So here's the model. I promised I would have a model. So that this is the risk neutral dynamics, right? So the increase in the index, which is xt here, in the S&P 500, say, is just the risk-free rate. So you have to subtract the dividend stream that we think of as deterministic in the short run. So it's just the compensation is the risk-free rate plus there's a stochastic volatility piece, and then you're going to have some jumps. We're going to model the jumps as double exponential. That means we start at 0, and there's a certain probability of getting negative jumps and certain probability of getting positive jumps at a certain magnitude. But we start at 0, which means when we let it decay like that, very large jumps are less likely than very smaller jumps. And empirically, people have this tendency of putting a Gaussian jump distribution in. It always goes to the left. And you would think very large negative jumps are more likely than small negative jumps or even positive jumps. It's not the case in the data. It's not what the option surfaces are telling you. So that's a bad modeling assumption. You're much better off doing this Koo trick. I think Steve Koo had these papers 15 years ago at least, where he introduced this double exponential. That seems to be much more in line with the data, so that's why we're using it. So there's going to be a double exponential jumps, different decay rates to the left and the right, because we know the skew, right? So the risk neural density will price jumps have many more negative jumps and many more large negative jumps than on the positive side. We're going to have a volatility dynamics, which is just a Heston model with squared co-jumps. So that's another feature that we learned from others. When there is a jump in the index, whether you can see it or not, there is a jump in volatility as well. Often you will see it very abruptly. So the best way of talking about jumps in volatility is actually when it happens, there's also a jump in the underlying. It's very difficult empirically to disprove that fact. And we hard code that into the model. And in fact, given that this is under the risk neural density, it seems that the volatility doesn't respond much to positive jumps, but it reacts dramatically to negative jumps. So we're going to only let the negative jumps feed into these jumps in the volatility. And we are going to square them, so that it's a pretty dramatic effect. It actually looks like a gauge model, an asymmetric gauge or something like that. So we get a shock to returns. It gets amplified into the volatilities when it's a bad shock. And so here we have the jump intensity. That's extremely simple. Look at that. It's a positive variable because you get a negative probability of jumps. So it has some level. It will mean revert all the time. But then it also co-jumps with the jumps up there. So occasionally it gets its shock up and then start mean reverting, gets another shock up and start mean reverting. And that's it. It's very, very simple. And these are all, there's only one jump, right? When this jumps, these other two guys jump as well. But they won't jump equally much. And they won't have the same persistence, and that's going to be important. And see, the persistence or the mean reversion of the shock to the jumps is going to be different than the mean reversion that I didn't show here yet, but they are going to be different, the loadings here. There's going to be a parameter that we allow for the typical leverage effect, right? So that these two shocks can be negatively correlated, and the jump intensities is C minus and C plus, so the jump intensity in the positive and negative jump intensity. In an affine model, they can be affine functions of the state variables, so that's what we write in here. Generally, that will give you a lot of parameters. Fortunately, when you go to the empirical work, it turns out that we can leave this constant. We really don't get much leverage. They're basically insignificant, the coefficients on V and U. For the positive jumps, for the negative jumps, well, we only find the loading on U to matter. The constant is essentially 0, so let's just zero them out and focus on what's really going on, and that is when there's this jump intensity is simply loading on the U factor, and that basically means it becomes the U factor. And I've been talking about the U factor as the jump intensity. That is only because of this empirical fact actually happens to work. But it has a really compelling interpretation, we think, and one of the factors is that negative jump intensity. Okay, here's writing out in the Grusham integral form what it means to have a negative squared jumps, that the co-jumps, we have a jump up here that's negative, then we square it and add it up. We have the loading on that, mu v and mu u, and we have some mean reversion, kappa and kappa u. They can be different from for volatility and jumps, which means in the long run the dynamics of those two, the levels of those two can diverge quite dramatically as we see in the data. Okay, this is just the how quick the shape of the negative and the positive jumps decay. So you'll have much more decay to the left, the negative jumps and positive jumps. All the yellow little dots here, the ugly yellow things, means there's a parameter. But we only get 10 parameters to describe this 2,000 options on a given day observed, thousands of times. And because it's an affine model and we have some good numerical ways of doing this, we can actually estimate the whole system using all these options. Okay. I'll just speed up. So I will. So I've talked about this already. So let me very, very briefly say what the estimation approach is. So we have these here. It's exactly the same as the first picture I showed you on the schematic form. So on a given day, we're observing a moneyness in one dimension and maturity in the other dimension of the options. These dots represent observations for that maturity and that strike price, and the dot will then be associated with a price. So there will be some price observation of that option. Now, if you're looking across time, you're going to have different options traded, and there's no way that this is balanced, so you have to have an estimation approach that wants to use all the options, but adapts to this particular feature. Like time is going this way, so you have 1,500 of these panels, and you want to use all the dots, all the prices of these options throughout the panel to estimate everything. Now, it looks like a hard problem, but what we're going to do is we're going to hold the coefficients constant. So they're constant across all these surfaces, but on each day, we're going to let that option surface on that day, conditional on the parameters that we're estimating, be extracted just from that day. So we're going to get a U and a V every day. So there's going to be different state vector here, here, and here, but the parameters are going to stay the same. I promised I wouldn't talk much about the estimation technology, and since I'm short of, it's not exactly on time?
Yeah, probably.
15 minutes, that's a bit better than 10. Okay. So there's nothing curious about the estimation procedure, and you can go in the papers and look at it, but the underlying mechanics is a bit heavy in tools. But the idea is very simple. So you want to estimate a parameter theta. I hope you can follow from over there. But there's a theta hat there. That's going to be our estimate of the parameter. And we're going to estimate ST, which is our state vector, the V and U, every day from observation 1 up to cap T. So we're going to estimate 1,500 bivariate state variables for each day we're observing this thing. And then a fixed parameter vector that's about 10 parameters or something like that that captures the whole surface. How do we do that? We want to minimize the error we do in a squared error sense between the model implied, and we get that from the affine model, that there is a essentially closed form solution, so we can calculate what the model implies given a parameter and the state vector, what should the options look like at different strikes and maturities, and compare that to the observed option prices. And you want to minimize that average. We're dividing by n, which means that's the number of observations on that day. That means, the end of 2014 is not more important than the beginning of 2007 because we're taking the average pricing error on that day. Otherwise, you tilt towards the part of the sample where there are a lot of options. But that's pretty simple. You're just minimizing squared error in the option prices, or these are actually the Black-Scholes representation, Black-Scholes implied vol representation of the option prices. That's a better way of doing it. There's a penalty term here which basically says, well, we're backing out with spot volatility. We can also estimate the spot volatility from the S&P 500 high-frequency data, and we can do it towards the end of the day. We can use an hour or two just before the end of the day. We can get a pretty precise estimate of what the volatility is. We can compare what we backed out from the option and that high-frequency volatility where it's actually stripped from jumps. It's a jump robust volatility measure. I'm not going to talk more about that, but it actually has no arbitrage condition that those two things, if you can measure them without error, should be identical. Because it's spot volatility, and the spot volatility should be the same in equivalent martingale measures. So it's basically. So you can use that to kind of penalize and robustify the estimation. It turns out to be somewhat useful. But honestly, you get more or less the same results if you just left that thing out. It just helps computationally, and it's kind of nice theoretically. Let me not talk more about that. Let's go to the evidence for the European indices. And I've written them up here, but you've seen them before. We apply very standard filters. I guess the most important might be that we don't use option prices unless they have a certain size relative to the tick size of the options, because, gee, if an option is worth 2 cents and we get a midpoint of 10 cents, it looks like a dramatic error. We just don't want to go there. But otherwise, it's pretty standard ways of doing it. So we apply that estimation method now for the 6 European indices that we have, and we compare them to the US. And so this is just the spot volatility, and this was a surprise to us as well. You could see that, so on each panel we had the S&P spot volatility extracted on a given day, and that for the E-stocks, which is a European index of large stocks in the euro currency area. And they are almost on top of each other. There's actually two curves here. And you can kind of see there's a gray and a black, right? The gray is the US and Euro stocks is the black. So once we come out of the financial crisis, they start diverging, and they're diverging very systematically with the E-stocks being a bit higher. So these are probably the sovereign debt crisis and the impact of that. But through the financial crisis, they were essentially on top of each other. Nobody should necessarily expect them to be entirely on top of each other. There's currency risks and other things in between. It's not obvious that they should be exactly the same, but they turn out to be. You know, let me not point too much to the other ones, except to notice when you get to Italy and Spain, again, you see they kind of follow through the financial crisis and then they diverge dramatically. This is Italy and this is Spain. So especially for Italy, you get much, much higher stock volatility based on the options than you do for the US. But that divergence only happens after the financial crisis. What about the U factor, this jump intensity factor, this negative jump intensity factor that people are pricing into their options? Well, again, let me do it over here so get to see me wave. So here you see that there's actually more of a discrepancy. You see that the E-stocks jump intensity is higher than the US pretty systematically, and the gap is wider. It's there for Germany as well. When you get to Switzerland, it actually goes the other way. The Swiss seem to have less jumps implied in the index than the US. And then you go to Spain. Look at Spain down here. Now there's an order of magnitude difference, not through the financial crisis, but after. And my simple interpretation is that people were talking about a southern Europe and Spain being completely separated from the Eurozone, which would have been a major shock. And people were seemingly kind of pricing that into the option surface. That would be a simple way of thinking about it. But, you know, they were more exposed to real estate. There were lots of things going on in Spain. Okay. So, very quickly, do we get the same type of qualitative findings economically that we did before? So here we have the return variation predictability. So this is where we are looking at which factor can explain what actually went on in terms of realized volatility or return variation in terms of risk going forward. We get the same picture as we got for the US. It's the implied volatility factor that can forecast return variation and risks. It's a pretty good thing. We can do it for 6 different indices. You get, you know, I'm not going to talk about the individual ones. You get exactly qualitative the same thing 6 times out of 6. Let's go to the returns, which is where we found, surprisingly, maybe, that this tail factor was the only thing that matters. Well, you can 6 times out of 6. Sometimes the significance becomes a little bit marginal, but the squared returns are good. Switzerland in particular is a very hard case because they have this imposition of a cap, and there's a major shock to the stock market in Switzerland because it had an impact on the exchange rate that kind of shook up the markets. They put a cap on, and later on they released it again. There were some really big shocks in Switzerland that was completely unanticipated. But you see the same patterns for all the other indices. You see the same square patterns. It is the tail factor in all of those countries, irrespective of their very different performance over this period, that robustly seems to correlate with their subsequent returns. So that tail piece that we identified seems to work, and certainly works much, much, much better than the old spot volatility factor. Okay. We have some reflections. This is a purely statistically driven exercise. We're finding this factor statistically. People, if you're a financial economist, you would like to think that there's a premium associated with that risk factor that projects future returns, and that premium would be varying around. So you can translate this into a negative jump risk premium and do the same exercise. What does that involve? You kind of have to find this jump variation, and you have to subtract the expected jump variation to like volatility and expected volatility, implied volatility minus expected volatility. Now, the realizations of really large negative returns are very tiny, so they completely overshadow what you see in the option surface in terms of the pricing of these bad events, especially on the left side. So what's going to happen is that we're going to get a noisy version of our tail measure coming out. And that's why this exercise really isn't as interesting as you might think. But it's still going to work, and I'm going to show you a little bit of competing this negative jump variance risk premium to the regular variance risk premium, so negative jump tail premium and the variance risk premium. I'm going to compare the two. In our model, I'm going to not go through the formal definition here, but what we do need is a negative jump variation measure, and we only have so far this U factor. In our model, it turns out the U factor maps directly into expected negative jump variation. The negative jump variation is the size of squared returns accumulated over a certain horizon given our current estimate of the U. And it's only going to be a function of the particular maturity you're looking at. So this affine structure gives us this very simple way of translating the intensity of negative shocks along with the exponential decay thing into a measure of what the expected jump variation is under that risk neutral measure. Then you'd want to subtract an expected measure which is almost zero relative to this, but can be a little noisy, and that would give us the premium. For the that noisy measure, you need a time series dynamics for that model. And let me not be using a very standard Haar model to predict what that would look like. But basically, the negative jump risk premium is going to look like this, which is very, you can see Spain goes crazy, right? You indicated that almost before. But otherwise, the pattern of this is just a little bit of a sharper version of what you saw before with the negative, with the U factor itself. So the U factor essentially translates into this with some noise. Okay, so we ran this horse race where we, there's more in the paper. I'm not sure these are the most revealing regressions, but we had one where we had the variance risk premium trying to predict future returns. And then we have the negative jump risk premium as just defined, trying to predict future returns over a horizon of 1 month, 4 months, and 7 months. Now, 1 month, we're not going to find much. Variance risk premium literature says you find nothing, we find nothing, so let's go to 4 and 7 months right away. There, the variance risk premium, well, it has R squares in the size of 1 and 2%, 0 sometimes. If you start adding in the negative jump risk premium, you start getting jumps to 11, 12, 14%. You get significant positive coefficients on the negative jump risk premium. The negative jump risk premium comes in and has explanatory power measured in terms of R squares or regression significance across all of these indices. Here's the 3 next ones. You should see this will be the Italian and the Spanish. R squares of 13 or 14% on these poorly performing indices. We can still kind of predict the variation in that over time. If you're just using the variance risk premium, you're getting almost nothing, marginal significance. And if you're just looking at this in the middle, this is the variance risk premium minus our tail premium. So that is the continuous part. It's all the rest of the variance risk premium. And here you're literally getting R squares that are, well, within rounding error of 0. So of the whole variance risk premium, the thing that forecasts these things is not the whole variance risk premium. It's just noise, except for that piece that's sitting out there in the tail, which seems to have all the predictive power. Now, that's maybe strengthening it too much, but economically, it seems to us that don't focus on the variance risk premium and all these variance swap contracts that's just looking at variances. Focus on what's being priced in the tail. And that might give you a much better sense of how to think about it economically. I have now 3-4 minutes. Okay. So let me not conclude on this. Let me jump right to Japan, because this is just Europe, and Europe is highly correlated with the US. And Japan is arguably much harder because people have tried to explain expected returns in Japan. It's been very, very, very difficult. So does our stuff work for Japan, right? And that's where Masato Ubukata comes in. He came and showed us that if you do this with Japan, it doesn't work. And we said, well, wait, you've got to focus on the tail. And then we found something, and then we had to think about it more, and then we found something we think is interesting and works. And that's what I'm going to do for the last few minutes. So for Japan, we're going to run the same average expected returns over a horizon of 8 months. This VT, this is bad. This is different location. This could be a vector of explanatory variables. It could be the tail. It could be the volatility. So these are the regressors. And these are the predictors for the future equity returns, right? Or it could be an RD or something. So instead of then going this highly parametric way where we're imposing a parametric model and we're backing out what U and V is, we're going to use other things that in particular Victor has been developing with Timboleslav on these non-parametric measures for left jump variation. Okay, so we're going to do this non-parametrically, and we're going to check with the US as well that we get results like we did before. So here's a list of a lot of papers that have tried to explain expected returns in Japan. The evidence is usually very non-robust. The R-squares aren't very high. People scratch their heads and say, why is Japan so different from all the other developed economies? It's very high. So what happened with Masato is that he had access to much better options data than we at that point had from the option metrics. We wanted to use Japan in our study that I showed you before. We couldn't because the options weren't good enough. Magically, he had much better contacts. Well, maybe naturally he had much better contacts because he's Japanese. So, so he had got his hands on these much better options data. And so we're going to try and use those. And basically the question to ask is, does this left jump variation measure that we can back out from these shorter dated Japanese options, do they also have predictive power for the returns? Very briefly, we are going to find that the variance risk premium, or the variance risk premium and this left jump variation premium in Japan and the US arguably are not as closely aligned as they were for the European countries. So there's more idiosyncratic or fundamentally non-correlated risk with the US than there were for the others. So it's an interesting place to go and look to see if the results will hold up. What we are going to find, and I may not have time to show it to you, so let me just say it, right? When you run country-specific regressions for Japan, so you run a yen Nikkei index or something like that, the excess return on that does not turn out to be that correlated with the left jump variation in Japan that you can back out from the options. So that's sad, right? It just doesn't work. So it works for Europe and the US, it doesn't work for Japan. You could pack up and go home, right? Now, of course, some of you know that the US measures are highly correlated with the ones in Europe. So some people have just taken the US measure and used that to explain what's going on in the other indices, even though they're in a different currency. And they usually get success. I think partially they're so highly correlated, maybe US is it's just like a global factor or something. So it turns out if we take that approach and just say, let's use the US measure of tail risk, then we get some traction. We can actually start explaining what's going on in Japan. Okay? And now that would be kind of a weird way to go about it, except for one important fact, and that's something that we learned in this study. The foreigners hold an enormous amount of fraction of the Japanese equities, and the trading of derivatives in the later years have been 90% foreigners and not Japanese guys. So you start thinking, okay, if these guys somehow dominate the pricing and they are foreigners, maybe they're using the US as a reference for risk rather than the Japanese index. But then we should also, you could look at the returns on the Japanese index in dollar-denominated terms in order to be consistent. I don't like mismatching the currencies. So what we're going to do is we're going to translate the Japanese returns with the exchange rate into dollar returns and then use the dollar index, risk index, tail index, to explain the Japanese returns. And that involves bringing in the exchange rate and thinking about whether the exchange rate can be partially explained by this, this left tail factor as well. And now I'm almost out of time. So let me more or less wrap up. So you can formally define these risk measures. There's a very, very nice way of extrapolating short-dated options into the tail using extreme value theory. So if you take short-dated options and you think extreme value theory is a very good approximation for the risk neutral density in the tail, the log prices should be linear, and you can actually, it works like a charm if you start doing it, which means you can actually measure this tail decay. When you get out of the money, you have to get into the tail a little bit. You can use part of the tail, and then you can extrapolate what the size of the tail is way out where you don't see much, and you can call that the tail. So you're extrapolating out. And that's essentially what we're doing. And it turns out we can get both the shape and the size of the tail time varying using this non-parametric procedure. We're using short-dated options. Okay. So that speaks to that weekly options are really, really useful in general. We're doing it for the Nikkei. We're going all 7 sigmas out of the money to define where we are on the tail. And Brian started looking at me. So here are the return regressions for the US when we do it. You should see this looks similar to the things we had before. After 3-4 months, you're very significant in the US, and that's what we had before. If you do it for Japan, you had 0. So it doesn't work for Japan when you take the Japanese things. Here's the amount of trading that foreigners do in Japanese indices. You see numbers over 90%. So it is really the foreigners who are setting the tone on those markets. If you do the dollar-denominated Nikkei return and you're using the tail measure for the US, it looks even better than it did for the US. So it seems to work with that twist that you now need to think of it as foreign investors driving the pricing in Japan. Now, there are questions that are brought up by that I don't know I can necessarily answer, but this seems to be quite robust fact. You can do a little bit with the exchange rate as well. You find marginal predictability. That means you're predicting the yen returns fairly well with the US index, but then you're also predicting the exchange rate, and when you combine the two, you get high explanatory power. And you restore, in fact, strengthen what we had for Europe in that particular sense. We could go back to Europe, and I'm sure it would work, use the US, and use a dollar-denominated return on those guys, and it would work as well. So let me conclude. We study return predictability in the Japanese and the European markets, and we find that this tail index does a great job. And since I'm out of time, I will leave it at that. Okay. Thank you.